what are some of the more unique or interesting challenges that you get to face in the design of and construction of tall buildings?
Well, I mean, the challenge is to try do something that's appropriate but unique and new. You know, we do a lot of different buildings. We never like to do the same one twice. You know, so how can you create using a different site, a different problem, a different part of the world, something that's appropriate and efficient and that's it's a good structure, but also is unique. And also, how do you sell your ideas? That's always very difficult. If you've got something that you think is really good, how can you convince the client and your collaborators that this is the way to go? So those are always difficult things that you have to deal with when you're designing anything, not just a tall building.
Sure. As you know, with this class, we're focusing on Fazlur Khan, and especially since you work at SOM, we were interested in what some of the structures or ideas that Khan had that most influenced you personally, and from your work in SOM, you think influenced the firm?
Part of it is not necessarily his designs as much as it was the environment that the office had, kind of his legacy within the practice. Now, he did a lot of his innovation down at IIT, Illinois Institute of Technology, in the College of Architecture. He and Maryann Goldsmith taught down there for years, and together they would, working with a student doing their master's thesis, in this case it would have been someone who already had a 5-year degree in architecture and they wanted to do a thesis, and they'd spend a couple of years doing one problem. And they would use that as a research field to try to develop new ideas and new systems. And like the John Hancock was originally a master's thesis. It wasn't tapered, but it was a straight up and down braced tower. And so they were able to resolve the technical issues there. And then, so when the problem, when the opportunity came, the design opportunity came, they knew that they could propose an idea with confidence. Now, I was, after Faz Khan passed away, I then started going down to IIT, and I spent maybe over a dozen years. Every Saturday I go down there and work with the students and Maryann Goldsmith. And that's how I helped develop my ideas, was through this process, this kind of this tradition that he created. And it's this whole close collaboration and a office that was dedicated to architects and engineers working together. And after he passed away, there was still Bruce Graham and Maryann was still there, and other senior engineers and architects in the firm who were of like-minded, so the traditions kept coming.
Sure. I guess following along with that, you were talking about his legacy of the cooperation between engineers and architects, and in your writing you also stress the importance of the collaboration with architects. So yeah, just wondering if you could elaborate more on that, and any specific things that you think you learn from architects.
I learn from architects all the time. The question is, what do we learn from working together with architects? It's amazing. One of my most important mentors was an architect named Jin Kim. I was working on a renovation of Sears Towers. My first project as a project engineer is that barrel vaulted entrance on the Wacker Street side. And I was designing this monumental stair, and I came up with a structure that worked, but it's pretty ugly. And Jin came over to me, and he was very upset with me. He was an architect. He said, an engineer should always design his structure so that an architect feels bad if he covers it up. And so it was that kind of challenging. And Jen and I went together to do many projects together, McCormick Place and also Exchange House in London. This kind of challenging each other to be your best. But this collaborative influence is where we don't have firm barriers at SOM where you have architects and engineers working together, and it's a self-selecting group. It's architects who like to work with engineers, and it's engineers who like to work with architects. You choose to be there. If that's not the way you work, you don't stay there. And so we never think twice about suggesting architectural ideas, and architects never think twice about suggesting structural ideas. Sure, yeah. And a lot of times we will counter-propose to each other. It could be something as like on the core of the Burj Khalifa, the architects would draw a core which would satisfy some of their needs, but not ours. So we would just draw our own core and say, try this one. And they said, no, it doesn't satisfy this. But by going back and forth by proposing, counter-proposing, we came to something that worked for both of us, better than either of us could have done by ourselves.
Right.
We also work in a collaborative manner where we have, when the job comes in the office, it's a white sheet of paper. There's no, it's not like make it work. There's nothing drawn yet. And we call them kindergarten tables, okay, like little kids where you draw. And we have these wooden tables, they're 5 foot square, and you can sit 8 people there. And so you all sit there at the table, and you have your trace, and you grab your pencil, and you fight for the pencil, okay. And so you have an idea, and you come to these meetings, and you have an idea, and you explain your idea, and they'll be listening to you, but they'll hear it through their own idea. And they, even if they try to repeat back to you what you said, it'll come out different, and it'll be something different than what you suggested. And so you come away from these meetings or these charrettes or design collaborations where at a different place than anyone was when they first came to the table, and you come up with something none of you could come up with on your own.
I was thinking about the Burj Dubai, and especially what you just, or Burj Khalifa, I guess. Especially as you were just talking about how in the later stages you were able to design it to be taller, but I guess because of the construction already gotten underway, you weren't able to get it to be that height. We were wondering whether you thought there's a limit on how tall buildings will get, and if so, what it is.
Yeah, okay, how tall can one go? One can go quite tall. The limit is not structural. It's probably economic, but the structural solution can address the economic. But we could easily, knowing what we know now, we could easily do a 1 kilometer tower for probably less expensive and faster than Burj, from what we learned there. But it's about addressing the issues of scale. Okay, you can't just, you have to invent new structural systems to achieve this. While the Burj was being designed and built, it was a boom time, and it seemed like every month somebody else would announce the world's tallest building. Okay, I wouldn't worry about it. I'd note it, and okay, that's nice. I'd go about my work. I'd just worry about my own project. And but one by one, they all got canceled. Some of them, they started foundations, they canceled them. Several of them, they did that. And so I started studying why buildings don't get built. It's interesting to know why buildings get built, but it's also informative to know why buildings don't get built. I think they don't get built if they don't have a clear idea behind them, where they're wasteful in materials, they're too big, they have too much floor area, they don't think about construction, they're too slow to build, and you have to address a whole series of things in order to get a building built. And you can't take the systems that we have today and just blow them up with a balloon, with air, and make them bigger, because they won't work. They'll fall out of scale. I think the system, the buttress core, is probably good up to 1 kilometer. Beyond that, I would change systems. I have some ideas how I would do that. Could one go to 1 mile? Yes. One has to think about the economics, but part of it is not building too much area. Some of the proposals out there had 10 million square feet of floor area. It's like, that's a lot of area to market. It's that's a very big paycheck, a very big check to pay for the construction. And so you have to balance these things. And very important is speed. Everyone says time is money, but time is also risk. The longer it takes you to build the building or to design it, the more things can go bad. Political things, economic downturns, and the like. So you need to think about speed and construction the entire time.
Right. Well, I'm sure if a mile-high building is built, SOM will probably be the first one to do it.
We hope so.
Yeah. We were wondering what role you think that tall buildings can or should play, especially in developing emerging urban areas or cities.
Well, the whole world just passed a milestone in the last few years, which is now 50% of the people in the world live in urban areas. It never happened before. And so with the whole issues of limited resources, the carbon issues, energy issues, density is a very good thing. Okay, density properly done. This means density around mass transit, so people don't have to have cars to go places. They can get there by convenience and economical mass transit, or you could walk to the store, to the grocery, to your work, and this implies density. Okay, And density generally implies tall buildings, not necessarily super tall buildings, but certainly tall buildings. And if you ever spend any time in Hong Kong or say New York nearby, it is the tall buildings that enables the high density that does lead to efficient use of materials and low carbon consumption. And so tall buildings are definitely part of the future and the solution. For me, the analogy is Sears Tower, okay, Willis Tower. When Sears moved out of the Sears Tower, they moved into the suburbs of Chicago, okay. Before they were in the building, here you have one building that has 100 acres of floor plate. There's 4.4 million square feet. That's 100 acres of floor plate on one city block. So, and it's close to the L train. It's close to the suburban metro trains. So everyone got their mass transit. Very little parking. So what do? They moved to the suburbs, and they end up taking basically greenfield sites, farmland, and turning it into buildings. Low-rise buildings, so you have to have more of them. Everyone has to drive to work, and so you have to have the highways to get you there. You have to have the parking lot. If you drive to work, your car probably has more square feet than you do. The average parking spot's 300 square feet. My office is 300 square feet. So density, serviced by mass transit is a good thing, and I think it's the future.
You talk a lot about New York and Chicago and those cities, but what about more of developing world cities?
Well, particularly the developing cities. And we do a lot of work in China, a lot of work in India, and very, very different places, very different political situations. But these huge migrations of people to the city, they could not do it without the tall building, and the subways. They have to build it all.
I'm going to switch the order of my questions really quickly because one of my later questions actually ties in really nicely with what you were just talking about. When you designed the Burj Khalifa, was sustainability a factor in the design?
We always design energy efficient buildings. That's just our nature. It's just good business practice. It's a good service to your owners. 2003, when we won the competition, the sustainable movement wasn't as strong as it was at this time. So we did what we considered good practice at the time. It's very energy efficient walls. You might notice it's a three point. It's a Y shape, 3 points. So there's a lot of self shading. So only 1/6 of the facade can be in direct sunlight. All the others would be in some either at an angle or shaded. There's how the building sparkles a lot. The sparkle is sun not hitting the building. Okay, so we have a lot of these 8-inch deep at every mullion, every essentially 5 feet or 4 to 5 feet. We have this vertical rib, which is stainless steel, which reflects light. Makes the building sparkle, but also keeps the light from getting into the building. We also do a lot of water harvesting. You say it's a desert, but it's very humid there, particularly in the summertime. It can be very hot and very humid, and so So when you do your air conditioning, you get a lot of fresh water just from as you dry out the air to use for the building, and so we capture all that water and use it in the building. A very interesting thing is we call it sky source sustainability. You actually go through a climate change when you get that high off the ground. It's like why does it snow on mountains? Okay, and this is kind of a mountain. I remember being in Dubai when we still had the personnel hoist on the outside of the building, so you go to the top on the outside. It was July, and it was unbelievably hot and humid at the ground. And around the 50th floor, it was pleasant, or noticeably cooler. And by the time you got up to 160, it was pleasant. The humidity drops, the temperature drops, the air is less dense, the air is fresher. And so what our mechanical engineers try to do is they try to pull the air from a high of, from within each zone. They couldn't pull it from the top all the way to the bottom, but they would take advantage of this thermodynamics of elevation because you actually get a substantial temperature drop from the bottom to the top. It is a climate change.
When you're actually inventing new structural systems, what do you have to consider, and what do you think about, and what's the general thought process?
You're solving a problem, okay, and so as you're solving the problem, you go back to first principles, and what can I do that'll its height. Like some of these buildings, you'll have we've done some proposals from some very tall buildings where with very little floor area. So you have to do something different. And so you need a certain amount of stiffness, a certain amount of inertia, a certain width, or base size, a certain height, but you don't want to fill it in. You want to create voids. So what systems can you come up to address these things? And one of the things I find helpful is that if you can give it a name, okay. So as you're trying to develop an idea or something, if you try to describe it and it takes like a sentence to describe, maybe you haven't edited your ideas down to clarity. So like my goal is to if you come up with something new, can you describe it with a noun and an adjective? Okay, if you can get your ideas that clear, then all of a sudden your design gets a lot easier. Your hierarchy becomes clear. What's more important than what else? What's the idea? You communicate to your team, this is what we're trying to do. So we came up with the term buttressed core, okay? The core speaks to the center hexagonal core, which resists the building twisting. Twisting is very important. But it's too slender to go to great heights, so we needed to buttress it. So now, what's the most efficient buttress? So you come with this, and Fazlur Khan did that too. Bundled core, trussed tube, frame tube. These are all, adjective and a noun. And so if you can distill your ideas down to that, then maybe you're onto something. A lot of engineers out there who get caught in the make it work syndrome. Architects gives them a problem and says make it work, and they'll just it's Band-Aid after Band-Aid. There's load path after load path. Well, that didn't work, so let's throw in the brace didn't work. Let's throw in some moment frames. Well, that didn't work. Let's throw in some core walls. That's, and then it becomes a hodgepodge, and the clarity and the vision's lost. And I think if you have a clear idea, it's probably easier to engineer, easier to build.
And along the same lines, when you're actually going ahead to build these new structures, what kinds of methods do you have to come up with, and new technologies do you have to use in order to build these structures, particularly the Burj Khalifa?
Well, what it really was on Burj is being aware of the state of the art in technology. We didn't want to have a system that required something that didn't already exist. Now, this was a conscious decision on the design team, is that we wanted to use conventional systems arranged in a unique manner. Okay, it goes to do you really want the building built or not? Okay. And if you get too bizarre, too complicated, it gets too expensive. A lot of times contractors are afraid to bid it because they haven't done it before. You can't get competitive bids. And so my old boss at Skidmore, he was a partner. He was a partner with Fazlur Khan. He worked on the Hancock and Sears with Faz. Hal Angar, he used to always say, don't draw anything unless you have at least one idea how to build it. Okay. And too often you'll see engineers will create designs and they've given no thought to construction. And because of that, the building becomes very expensive. So we always have at least one idea how to build it. Now the contractor may have a better idea than they usually do. But on Burj, we know a lot about formwork construction because we've done a lot of tall buildings. And so we were very, very conscious on the formwork, getting to everything's modular and the like. My company's Skidmore, Owings Merrill. The initials are SOM, but we also say that stands for stay on module. You establish a grid, establish a module, and live with it. Okay, and it's easy to walk away and you make everything a special condition, but it's a discipline you put on yourself that you're going to stay on the module. And because of that, we were able to reuse some of the formwork about 160 times. Because even though the floor plates all varied, but vertically they're identical. So these pieces could go all the way up, and you just add on to it. In many ways, what you could look at as if you took the largest floor plate and you extruded the whole thing, and then you just trimmed it, and that's the final shape.
Earlier in your talk this afternoon, and in the papers that we read that you had written, you talk about how you rely on hand calculations for the initial design phase. Beyond saving time, how do computers factor into the design phase, especially with the Burj Khalifa?
The computers are important in verifying your hand calculations and also looking for nuances. Sometimes when you're doing your hand calculations, you look at the big pictures, but you'll find some funny little things going on. As you study the hand calc, I'll be curious as if you find some of the things that I'm aware of. I won't give you any clues. So anyway, so how do these things? And so the computer is very useful in that. There are certain things that you really can't do by hand. The construction sequence is very difficult, very time-consuming to try to do that by hand. And in the end, your detailed calculations, all the load transfers, the creep and shrinkage studies, and these are all things that you definitely need the computer for. But what I'm urging is that when you're in the conceptual design phase, when you're really trying to think about the design, you don't need millions of numbers. Okay, you need there's certain basic parameters like I talked about today, on the behavior. How much does it move? What's the load pass? Do you have uplift or not? How are your gravity loads moving? How can you use gravity as your friend? You use gravity to resist the wind loads. So gravity is very reliable. Okay, so use it. It's more reliable than almost anything else you have out there. And pull all that together, and then when you get the ideas, then definitely go to the computer just for verification and nuance studying and parametric studying, but not during the conceptual phase.
So we talked a lot about the Burj Khalifa and its structural systems and itself, but what do you think of Dubai as the context for the building?
Dubai is a very interesting place. It's a global city, or it was during the boom. It's a place like no other. It's what Singapore is to Southeast Asia, which is it's a business center that allows you to get out to all the surrounding regions. It's that and more to the Middle East and India and Pakistan. If you look at the list of exiled leaders, they all live in Dubai. Okay, some Chechen or some Pakistani who's on the run, or they all live in Dubai. It's the place where everything comes together. And at the time of the boom, it was full of 20-somethings from all over the world, having a great time, putting things together. Now, let's talk about, there was a lot of buildings that were built which are probably not necessary. The city is somewhat hard to get around in many places. The Burj development actually works. It's actually a very pedestrian zone in the middle of the city, because you can walk from the Burj to multiple hotels and the shopping malls and restaurants, and you can spend your whole time there without actually having to get in a car if you stay within. And there's another, our client was EMR. They also did a very similar place called the Marina, down where this infinity tower, this one that turns 90 degrees that we designed. And so those two, they were very good at creating, doesn't necessarily tie into the rest of the fabric in the same way, but within these are all very, very large developments, like one square kilometer type piece of land. But within the development, you can actually walk, which, one would hope you could always do that, but in Dubai, it's sometimes difficult to walk across the street, but in the called the Old Town Burj Dubai area, it's a very, very walkable, it's a pleasant place to be.
Going back to your work with SOM, what sort of problems do you anticipate in the future of super high-rise buildings based on your work?
Well, part of it is it's funny, for years and years and years, skyscrapers were just a little bit taller than the one before them. If you look from the Empire State Building to Taipei 101, the growth was really pretty small. And one of the things I found, now that we've done this giant leap, we've added 1,000 feet to this system, or 300 meters, everyone thinks that it's easy, and people say, oh, I want a 700 meter tower, I want a 600 meter tower, I want an 800 meter tower. And I do you really, there's a reason it took so long to get out of that, beyond that limitation. And so I see a lot of, I'm very surprised at how people think you can just buy it, you know, and that it's not a tremendous amount of effort and a lot of intellectual capital to actually make it successful. And so this is one thing that's going to surprise me. I see a lot of requests for proposals for super tall buildings. Okay. And I see a lot of them that go down the route of that list of buildings that never got built. You know, a lot of times I can tell when a design's DOA, you know, that it's not going to happen. But you know, they can spend a few $100 million discovering that it's not going to happen. But
okay, looking back on your education, in your article, Engineering an Idea, the Realization of the Burj Khalifa, you mentioned that your time spent working influenced your choice of classes, which later influenced your career. And what class do you think was the most important to your career?
Okay, well, you know, I graduated from the University of Missouri, and then I went to work for 4 years in the oil patch, okay, working on various things, some of which was structural related and construction related, but, and I discovered I didn't know anything, okay. And I was a pretty good student undergraduate. I took, you know, lots of classes, but there was huge holes in my education. So I went back to grad school with fear in my heart, and so I knew I needed to learn a lot. And one of my I went to Illinois, and one of my professors, Narby Kacharian, very, very good professor, he said theory is practical, you know, the more, and he was right, the more theory you know, the more, the more you can do, the more practical. And so I did all my coursework for the master's degree, then I spent another year just taking classes, and I do it again, I'd take even more classes, okay? I'd lean towards the theoretical classes, the ones that are related to behavior. I'm not sure I actually took a design class in graduate school. I don't think I did, like steel design or concrete, but I took several classes in concrete behavior, several classes in steel behavior, like why do they fail? Okay, well, you know, we work all over the world, you know, and so we use all kinds of different building codes. In China, we use Chinese building codes. Spain, we use Spanish building codes. And so it doesn't matter what's an AISC or ACI. It's what is the failure that you're trying to avoid in your design. And by understanding those, then you can adapt to these. And then knowing theoretical mechanics, theory of shells, theory of plates, theory of elasticity, energy methods. You know, finite element, nonlinear finite element. You know, understanding these things, you know, it gives you a pretty good toolkit to go forward. Now, you asked for my favorite class. That's a tough one. Interesting enough, it was two-way slabs, okay, which sounds pretty mundane, but it was taught by Meta Sozin, who was in Illinois circles a very famous professor. Now he's emeritus at Illinois. Now he teaches at Purdue. And it was called two-way slabs. It was actually theory of structures. And basically it was about think big, don't worry about the numbers, think about the behavior. You know, you know, he would do all these studies like two-way slabs, like how do you spread the rebar. Figure out what the moments are, figure out what the forces are, and then figure out how much rebar you need in total and just try to get it in the right place. You know, because the load will find it. If the load path is there, if you provide the load path, and maybe it's not the load path that the structure initially wants, it'll find it, okay? Because that's the one you provided. And you know, and this is often true. Bill Thornton, who does a lot of papers on design of gusset plates, okay? As long as there's not a brittle failure in the way, you know, you can make all kinds of assumptions as to how you design a gusset plate as long as you're consistent. And it'll work because, you know, as long as there's not a brittle failure in the way, it'll eventually find that load path. And so, you know, two-way slabs, but subtitle theory of structures, or no, structural philosophy is two-way slabs, subtitled structural philosophy.
So, based on your experiences, your educational experiences, what advice do you have for students who hope to pursue careers in structural engineering?
First, you got to go to grad school. That's not an option. Go as long as you can. If you and I strongly urge you not to pay your own way. get a TA, a teaching assistantship or a research assistantship, get an office in the building. So you're sitting around with the other grad students, helping each other out, talking about things, talking about life, talking about engineering. The professors are walking by, you can ask them a question. I remember, Professor Sozen used to take me out for a beer, okay? And you hear about the war stories about, why this didn't work and that didn't work, and, the things that don't fit into the classroom. And also it's important to learn from your colleagues. When you get out, this is not about school, but I remember Bill LeMessurier, who's a very, very great structural engineer. I used to see him at conferences, and one time I read one of his papers, and I had a bunch of questions, so I called him up. And we spent like an hour or two. I'm from a different firm. He talking about the theory and stuff like that, what's behind this thing. And I used to see him at conferences, and he would take me out for drinks. He'd go buy me a scotch. And then you hear the real stories, the stuff that's not published, what really happened, and this problem and that problem. And so it's I don't know, we call it folklore engineering or whatever, but so it's developing these relationships and the things. So go to school, take as many classes you can, emphasize the theory, but learn from your colleagues and your professors.
Yeah, we appreciate you for
Okay, well,
talking to us.
glad to be here. Had a nice day.
Yeah.
All right.